In this presentation, we will continue to talk about thin lenses, and we will look at some of the properties of thin lenses as well as how we can use geometric optics to determine where images are formed from a thin lens. So before we jump into talking about geometric optics, we need to understand some of the key features of the thin lenses and how images are formed. So the first thing is the principal axis. And the principal axis is essentially just a line that passes through the center of the lens for all practical purposes. It's the line that passes through the center. It's a line that joins the center of curvature of the two lens surfaces. So the lenses do have some curvature associated with them, and you can imagine that if this were a sphere, there would be some center of that spherical shell, and that's the center of curvature. The focal point is the point at which the light rays come together. We talked about that earlier. So basically, if I had light coming in parallel, it would all bend and pass through that focal point. And for a converging lens, the focal point would be on the opposite side of the lens as to where the light is coming in. And there's a focal length, and the focal length is just the distance that is measured from the center of the lens out to where the focal point is located. So we can use the principal axis, and we can use the focal point and also the center of curvature, more specifically twice the focal length, and we can draw some rays of light that come from the top of an object that's placed near a thin lens, and using 3 different rays of light we can determine where the image is going to be formed. So the first, and I'm going to show this in a picture, but I'm going to talk through it first. So the first ray of light leaves the top of the object, travels parallel to the principal axis. After passing through the lens, it bends, refracts, and passes through the focal point on the opposite side of the lens. Ray 2 leaves the top of the object, passes through the focal point on the left side of the lens, the same side of the lens that the object is located. When it reaches the lens, it refracts and bends so that it travels parallel to the principal axis. And then there's a ray of light that starts at the top of the object and passes directly through the center of the lens and the principal axis without bending at all. So here is a picture. Here is my thin lens. You don't actually see the lens, but this is a converging lens, and this line represents the center of the lens. So here is my object, and it's located pretty far from the lens. So I've indicated the focal points and twice the focal point. So the focal length is the distance from the lens to that focal point, and then I've described another distance which is basically double that distance. So I have a converging lens, and I'm pretty far away. I'm a distance that's more than twice the focal length from the lens. So the first ray of light that we would draw comes in parallel to the principal axis, which is just the line that I've drawn here that has all of the focal points on it. And that ray of light would pass through the focal point on the other side, because remember, any rays of light coming in parallel will pass through that focal point. The second ray of light passes through the focal point that's located on the same side of the lens as the object, and when it strikes the surface of the lens, it refracts and passes parallel. This is basically like the principle of reversibility. So if the light was coming in from the other side, reversing it, it would pass through the focal point. And then finally, I have a ray of light that leaves the top of the object, passes through the center of curvature, passes through the center of the lens and the principal axis and just continues straight without refracting. So it turns out that where those rays of light come together, they form the image. And the image starts off as being located on the principal axis, and then where those rays of light come together is where the tip or the top of the image is located. So there's my image location. So one of the things I notice about this is that when my object for a converging lens is very far away, past twice the focal length, an image is formed. That image is going to be inverted, and it's also going to be real. Real images are formed when the rays of light come together and actually meet at a particular point, just like spherical mirrors. The rays of light come together, And so the image is inverted and real, and if I look at the size of this, it's actually smaller than the height of the object. So it's real, inverted, and smaller. An example of a converging lens that we are probably familiar with that uses an object that's pretty far away is the human eye and also cameras. And so the human eye has a converging lens in it. That converging lens is actually flexible, and you have muscles on both sides of the eye that can adjust the curvature of that lens, and which will change the focal length and will allow you to focus on objects that are very far away and also objects that are a little bit closer. But in general, you're still far from the you're over twice the focal length away. Same thing is true about a camera. The lens in a camera is not flexible, but it's movable. So you can adjust the location of the lens back and forth, which allows an object that's closer or further away to be focused on the film in the back. The important thing too here is to realize, look at the film, the image is inverted, right? And so when our eyes see an image, that image is actually inverted on the back of the eye, but our brain knows that that's how our eye works and interprets that and flips that around in terms of our brain seeing the image, seeing the object, I guess. I can now also move the object so that it's closer to the converging lens. And so if I move it so that it's between the focal point and twice the focal point, I can draw those rays of light again. So I have ray 1 coming in and parallel passing through the focal point. I have ray 2 passing through the focal point on the same side of the lens as the object and passing, refracting and going parallel to the lens. And then I have a ray of light that comes in and passes directly through the center of the lens and the principal axis. And where those rays of light come together over here is where the top of the image is located. And the image starts at the principal axis and goes to that point. So here is my image for the case where I have a converging lens, but the object is moved closer so that it's between the focal length and twice the focal length. What I notice is that I have an inverted image again. So it's the opposite orientation as the object. It is larger, so the size of this arrow lengthwise is longer than this one. And it is also real because the rays of light actually come together where the image is formed. One of the things that we'll see is that if an image is inverted for converging lenses, it's always real. Converging lenses can form images that are real or virtual. We'll see that in a minute. But an example of this would be a slide projector or just a projector in general. So if you've been in a classroom where they use a projector, the image that you see on the screen is very large, but inside the projector, what's being projected behind that lens is actually very small. It's not inverted on the screen because the object inside of the actual projector is inverted so that we see it as upright. Finally, I can take a converging lens and I can move the object so that it's between the lens and the focal point. And in this case, the image formation is different. So I have a ray of light coming in parallel from the top of that arrow. So remember, and I should have started with this, that rays of light leave the top of our object in all directions, right? Every direction. And we're looking at just 3 of those rays. So the first ray comes in parallel, passes through the focal point. The second one seems to pass through the focal point, but it can't do that. So it's as if it was coming from the focal point and going from the top of the image, and then it goes parallel after passing through, and then the last one passes directly through the center of the lens and the principal axis. And one of the things that's important about this particular situation is that these rays of light never come together, right? They're diverging from one another. So if I want to be able to see the image that's formed by this lens and this object being placed near this lens, I am going to have to follow these rays of light back. So I follow them back, and where they all seem to be originating from is where my image is formed. So to see this, I would have to have my eye over here, and I would have to look through the lens. So I place my lens down, I bring my object close to the lens, my eye sees these rays of light, and those rays of light seem to be originating from behind the lens at this location, and my eye interprets that as where the actual image is located. So this is a virtual image. It's virtual because the rays of light don't actually come together. They seem to diverge, but to see the image, I have to bring those rays of light together to a particular point. The image is upright, and it is larger in this particular case. So converging lenses can form virtual images as well as real images. If an image is upright, it's always going to be virtual. This type of an image can't be formed on a screen. The only way to see it is to look through the lens to see the image. So this might be something like a magnifying glass. If you use a magnifying glass, you can put the object behind the glass, you look through the magnifying glass, and you see the image, which is much larger. So here's where the eye would have to look to see that particular image. Whereas in the other examples, we could form those images on a screen and the eye could see it at any location. So here's that example again of the of that lens, and here's a nickel and how it would look when you look through that lens. It's magnified. If we talk about diverging lenses, with diverging lenses, we can do the same type of a thing. We can look at three rays. Ray 1 leaves the top of the object, travels parallel to the principal axis, but after it passes through the lens, it refracts away from the axis and seems like it's originating from the focal point on the left. I'm going to show an image of this. Ray 2 leaves the top of the object, moves towards the focal point on the right side of the lens, but after passing through the lens, it actually travels parallel, and then the third one, just like converging lenses, passes directly through the center. So let's look at an example of this. So the first ray of light goes in parallel, and then it seems like, so it diverges when it passes through that diverging lens, and that ray of light seems like it was coming from the focal point on the same side of the lens as the object. So that's ray number 1. Ray number 2 heads towards the focal point on the opposite side of the lens, so it's heading towards the focal point on the opposite side of the lens, but when it hits the lens, instead of going to that focal point, it travels parallel to the principal axis. And then the final ray goes directly through the center. So once again, in this particular case for the diverging lens, the rays of light always diverge from one another. So in order to see the image, you have to follow the rays of light that pass through the lens. So the blue ray, the red one, and the green one, I have to follow those rays of light back. So if I make dotted lines going back, I've got a ray of light going back here. For the red one, I would have to follow it back, and I put a dotted line here. And then for the green one, they would all meet at this particular location. So it appears as if all of these rays of light are coming from this point behind the lens. So our eye would have to be over on the right side of the lens, and they would see an image formed over here behind the lens. So there's my image location. So this image is virtual, upright, and smaller. So diverging lenses always form virtual images, and they're always going to be smaller. Anytime you have an upright image, it's also always a virtual image when we're dealing with lenses. So the only way to see an image that's formed by a diverging lens is to physically look through the lens, and then we can see the image. So here's an example of a diverging lens with a picture. You can obviously tell there's a person back here, and by looking through that lens, we can see that that image is actually smaller than the size of the object. So which of these lenses should be used for someone who is nearsighted, and which one should be used for someone who's farsighted? a nearsighted person can see objects clearly that are near but not far. So the lens would need to move an object's image closer to the eye. So you'd need a diverging lens. So if I go back a second here, let's see if I can go back. Over here, I have an object that's far away. Now, someone who's nearsighted can see near but not far away. So when the person looks through the lens, they see the image as being closer to their eye. And so a person who is nearsighted, can't see far away, would need to use a diverging lens. A person who is farsighted can see clearly far but not near. They would need a lens that could move an object's image further away so that they can see it because they can see far. So they're going to need to use a converging lens, which was the third case of the converging lenses that we saw. So just to show very quickly, there is a PhET simulation with geometric optics that can show how images are formed. So here's my converging lens. Here's my focal point. So if I were to measure my focal point, I would measure the distance from the X to the center of the lens. I'm going to say it's probably around 64 centimeters, right? So here's 60, here's 70. It's kind of hard to read, but it's probably around 64, 65 centimeters. And the location of my object over here is about 200 centimeters. So I'm far away from the lens, and I form an image that is inverted and smaller when I'm far away. As I bring the object closer so that it's within twice the focal length and the focal length, which is definitely here. So now my object is here, it's upright. My image is inverted and it's larger. So that was the second case that we looked at. And then finally, if I bring the object so that it's within the focal length, I can't see the image anymore because all of those rays of light diverge. But if I say show virtual image, if I follow those rays of light back, I can now see that image, and I could measure, where it's located relative to the lens as well, sort of over here. So my image distance would be the distance from my object, my object distance would be the distance from my actual object to the center of the curvature, or the center of my lens, and then my image distance would be the distance from my image to the center of the lens.